Hello. Today I'm going to present on an algorithm that I did. Um, it is done using Java and it is using dynamic programming, aka caching, in order to achieve a better performing algorithm. The algorithm that I solved for was counting play combos for a given final score. And I found this in my Elements of Programming interview for Java book. So the the first thing I can do is explain the problem. So if we have something like football where our play scores are 2, 3, and 7, and we have a final score of 16. Well, the idea is what are the number of of different combos of plays to get to that score? And very simply, one right off the bat would be 2 times 8. So the 2 play score 8 times. Another one right off the bat would be um, 2 once and 7 twice. So here's a count of 2 combos of plays to get a score of 16. There's more, but I'll just keep going because I don't want to show all of them. What I'll do first is explain the brute force algorithm, and then we can get into the better dynamic programming algorithm and compare performance. So the first we'll think a bit more simply. So what if there's an A score and a B score? There's just or an A play that results in a play that results in A points and a play that results in B points. So just 2 plays. Well, number 1, we can have just combos of A, just combos of B, and then combos of A and B that result in our final score, and we want to know if we want to know the different combos of A and B to get to the final score. So A just A's is fairly easy. We can just keep adding A to itself, and if we hit final score on the nose, then we can add to our matches count, if you will, um, and do the same for B, right? Well, with A, combinations of A and B that result in final score gets a bit more complex. So let's say we have 0 on one end and our final score over here. We can start A at just A. And then from this point we could say we can have B start at just B and then march B so that it keeps on adding to itself until we either hit or go past our final score. And if we do hit it on the nose, and find a combination of A and B that is final score, then we'll say increment matches count. And then we'll do the same, kind of the same thing, but we'll march A to 2A, and do the same thing with B, marching B, right? And we keep doing this until we get to having 2A be either equal the final score or greater than final score. Once we get there, then we stop our iterating, because we can't possibly have another combo of A and B and determine if we can increment our matches count. So this looping, which looks kind of like this if you look at my cursor, where you have you increment A one step and then do, you know, multiple B iterations, so like a sub loop, and then you do another increment of A and then a B sub loop, another increment of A, B sub loop, and so on until you get to the end of the double looping. That complexity is big O n squared. And I know this just because there's a bit more of a fine-grained math equation for that pattern, and it is n times n minus 1 over 2. It may be n times n plus 2, or n times n plus 1 over 2, but we're dealing with big O notation, so it doesn't matter. This, in big O notation, boils down to n squared or quadratic complexity. So, how do we improve upon this? What we do is give a hash set for A scores. Right? Let's say A is 2, B is 3. Well, we do one iteration of A from 0 to the final score, right? So it's, first it's 2, then 4, then 6, then 8, and so on and so forth to the final score. And we cache them here, 2, 4. Right. Then all we need to do is march through B the first value for B is going to be 3. We get the difference between final score and 3, and we see if that value is in our A combo scores hash set. If it is, then we can increment our matches count. And then we march the B sum for B plays to the next iteration, and we do the same diff solving, see if it's in hash set. If it is, we increment matches count, and we keep doing that. You can see very clearly that we're only doing one end loop, another end loop here, and we have 2n, which boils down to just big O n complexity for time, and then plus big O n for space, right? Because this is going to be 2, 4, 6, 8, and that amount is the amount of marches that we do, which is what n is. The marches are they're the average amount of marches for the set of plays that we're doing our algorithm for. Okay, so we're I bet that I bet now what you are wondering about is how we have that how we go from here to the finding play combos where it's 3 plays. And we could here, I'll get a bit more canvas here. We could get hash sets for both A and B, and if you imagine both those, right, we could do, and like A would have 2, 4, B would have 3, 6, and we could do a double loop through through our plays here, right? So start here and then loop through all these, and then have an A-B cache, right? So 2, then 3, so 5, 8. And then iterate here, and same thing there, 12, or no, not 12. Seven, 10. But this complexity is big O n squared, right? So we could do this in order to then use our AB score our AB play combo cache to then do the iterating through C and seeing if we have any matches again, do that same process like we did for A or for B against the caching of A, but C against the caching of AB, right? But what I was thinking was we could just use I think the brute force for getting ABC score combos is better. Or for building the AB cache. So we're still having n squared complexity and iterating through our A and B caches to build the AB cache. But we have the extra space, right? So why not just do the original algorithm for getting A/B score combos by marching A and then plus B times 1 and then B plus B times 2 and then so on and so forth, and then do A times 2 plus B times 1 plus B times 2 and so on and so forth, and do that same brute force for iterating through A/B score combos to build up the AB cache. That means that we have the same complexity, like I was saying, in terms of time, but that way we're not doing the extra space complexity here. So that was one thought that I had. The one other aspect to mention that's important is doing this for building up to getting ABC score combos, and iterating through the C values, getting the diffs against final score, and seeing if there exists a match in the AB cache, which has n squared complexity, is better than the brute force of ABC using the brute force method, which would be going from 0 to the final score. It would be put A here and then do the n squared complexity for BC combos in this area. So B and then C and then B and then C, right? So it's n squared complexity for every march of A, so that results in big O n cubed for brute force of A, B, and C. And you can see how if you do the building of the AB score combos cache, then it's just a running through, like I was saying, of the C building, just one linear loop through C combos and seeing if there's any matches against AB, and we've achieved a increase in the performance complexity from going from n cubed to n squared. Okay. I think that's it. All right.